What's going on, smart people? Today we're going to be ranking some famous physics equations. Now initially I was going to make a list of equations myself and pin them against each other, but it turns out our friend Eric Aspling from Physics Office Hours already beat me to it, so we're going to be using his list instead and ranking those equations. You can find a link to his YouTube channel in the description, and thanks again, Eric, for letting me use your list. Now I have to say this because if I don't, people will get weirdly angry about their equations not being ranked higher that they like. This is subjective. Whatever emotion is most dominant when I look at a specific equation is probably going to be how I rank it, so just take that with a grain of salt. Really, this is just an excuse for me to talk about equations that I like. I'm not just going to be quickly putting them in certain categories. I'll be talking about them and maybe talking about the history of them or the importance of them, things like that, so we're just going to try to have a good time. Okay, now with that being said, let's go ahead and get started. Now I glanced briefly at these equations just to make sure that they were, but other than that, I don't really know what all is on here, but I do see some heavy hitters up on this first line, so let's start here and work our way left. Okay, so we're starting off with the Lorentz, I hope I know all, that would be embarrassing if I don't know all of these equations. We're starting off with the Lorentz Force equation. This is a pretty cool one. So this describes if you put a charged particle in an electromagnetic field, how does it move? This is important for a few reasons. Like in particle physics, if you put an electron or a positron in this, and you slap it with a magnetic field, they will bend, they will curve in different directions. So it's nice for particle identification. If you measure the radius of the curvature and you know the strength of the magnetic field and you measure its acceleration, things like that, then you can extract the energy of the particle as well. So it's a pretty important equation. Not only that, but it's also relativistic by kind of accident, right? Like if you were to write down a Lorentz invariant Lagrangian for electromagnetism and you solve for the equations of motion using Euler Lagrange equations, this is the 3/4 that you get. So it actually, you may not know that, but this is relativistic, which is, I think, kind of cool. It's not like an amazing equation. I don't think it's S tier, but it's overall pretty well rounded. So I think I might actually put it A tier. Why not? The next one, I can't read this, but I think we all know, if you've looked ahead in like particle physics, you probably know what this equation is. This is the standard model Lagrangian. It describes the 3 out of 4 fundamental interactions of nature, the electromagnetic force, and then the strong and weak nuclear forces. Talks about why the Higgs be like it do, but it does not have gravity worked into it. Personally, I think this equation is kind of hideous. I think it's disgusting. Maybe if it described everything, like it's like, guys, this is pretty gross, but it works for everything, then I would rank it higher. But, aside from the obvious things, like it doesn't have gravity in it, it doesn't describe dark matter, there's other stuff about it too, like incorrect initial predictions, like that the neutrinos are massless. It's a model, and like all models, you can tune parameters and put things or take things away by hand. So I think they have ways of like fixing that stuff, but I think the standard model Lagrangian is kind of gross. Granted, this is in like a super expanded form, but yeah, I'm not a huge fan of how it looks, but it is pretty powerful. Like I said, it does describe E&M and the nuclear interactions. So I think I'll put it, this is probably blasphemy because I work in the realm of nuclear and particle physics, theoretical, so like this is stuff that I see, but I think I'm going to put it B tier, which is probably going to piss some people off. Moving on from that, we have the Schrödinger equation. It describes our non-relativistic theory of the electron. So this is cast so it slaps you in the face that this is an eigenvalue problem. You have a differential operator acting on a function, spits back out the function times a number, and that number is the energy of the particle. Super iconic equation. When I was in undergrad, I couldn't wait to learn about it. It just seemed like this this mythical thing that was the crazy frontier of physics that I couldn't wait to try and wrap my head around. And it is pretty cool, and then you find out that there's only like a handful of problems that you can solve by hand, and it's not particularly fun to solve, but it is super iconic, and it works reasonably well. And I mean, sure, there's ones that you can only solve by hand, but that doesn't mean you can't solve the rest numerically, so it is a pretty powerful tool for non-relativistic quantum mechanics. I'm going to put this for because of how iconic it is, I'll put it on A tier as well. Ranking the Schrödinger equation above the standard model Lagrangian. Okay, the next one is Ohm's law. The voltage is equal to the current times the resistance. Honestly, I don't give a shit about Ohm's law. Electronics is kind of cool. I know that there's people pushing aside their Arduino boards right now to type a comment about how it's the coolest thing ever. I don't use it, so I don't really have a deep appreciation for it. I haven't used it since introductory physics, so... well, that's not entirely true because I did take like an electronics course. So, I mean, if that's your ball game, then you'll rank this a lot higher for sure. But I'll probably put this in... Something's got to be D tier. I'll put it D tier. I don't care. Okay, by the way, if it looks like I'm sweaty, it's just the sweat. It's 97 degrees in New Mexico, and we still use swamp coolers like the Pilgrims did, so forgive me. The next thing is Noether's theorem. Differentiable symmetry leads to conservation laws. To me, that's one of the most important concepts in physics, period, if not the most. I mean, the conservation law alone, like if you can identify something that's conserved, it almost always means the equations you have to solve are easier. And how symmetry leads to that, I think, is just a beautiful thing. Some of you may be thinking that's not an equation, that's a statement or something. You can kind of phrase it in an equation, though. You can say the divergence of the conserved current is 0, and you can express that conserved current in terms of the variable that parameterizes the symmetry transformation. So you can kind of make it an equation. Damn, do we already have an S tier? I really think that this is pretty important. I think I'm gonna. For one, it's not just limited, it's very ubiquitous, right? It's not limited to just classical mechanics. You use it in quantum field theory, you use it everywhere. Anytime you have a continuous global symmetry. So that's pretty big. I think that's a reasonable, I don't think too many people would disagree with that. Okay, next we have Newton's law of universal gravitation. The gravitational force between two massive objects decreases with the square of the distance between them. The thing that sticks out about this, that's probably the first inverse square law that you see, which is kind of iconic, I guess. And if you don't know, the reason these inverse square laws happen is because if you have field lines coming from a source, if you put that source in a bubble, and then you increase the size of the bubble, the same number of field lines is going through that bigger bubble. But the surface area of that bubble increases with the square of its radius. So if the flux is going to be constant, then that means the field has to decrease with the square of the distance, which is why you get 1 over r squared for the field and the force. So that's why it seems like inverse square laws are everywhere. Historically, it's very important. Like I said, first inverse square law. Here's Newton's second law. You can cancel the first two masses and calculate the acceleration due to the mass of object. So that's like a pretty cool first exercise if you want to calculate that g on Earth is 9.81 meters per second squared. So it's cool. It's a cute thing to like first be exposed to. I'll probably put it. I'll probably put this in C tier and then Newton's second law in B tier. I never use it, even for like regular mechanics problems. I hardly ever use Newton's laws. I like using Lagrangians. Not because it's like, oh, look at me, I use Lagrangians. It's just because when you work with more complicated dynamical systems, Lagrangians become more practical. And for me, I don't want to have to make a decision of like, should I try to solve the problem this way or blah, blah, blah. I'd rather not be average at a bunch of different formalisms, like Newton's formalism, Lagrangian, Hamiltonian, Hamilton-Jacobi. I'd rather be really, really good at one. So I chose Lagrangians and kind of stuck with it. But Newton's law, yeah, it's very, historically, it's very important. Gave us this notion of force. It's just not, it didn't age well for me. You know, it's not something that I use very frequently. So I'll keep it at B tier. I can't read this, and it's not like the standard model Lagrangian where I know what it is just by how long it is. It looks like 3 equations, so maybe it's like components of a vector equation or something. I don't know. Maybe we'll have to come back to that. If it's specifically writing out components of a vector, maybe it's not relativistic because you could write that in like a very concise way. So yeah, I don't know. So it's probably not a wave equation or something. Next, so maybe we'll come back to that. Maybe context of the other ones will tell us what this one is. Next, we have Maxwell's equations. It's a little interesting because it's kind of mixing vacuum and in medium. So we have like the divergence of the electric displacement, the magnetic induction, electric field, and then the magnetic field. This is a really important equation, and I like that it's in differential form. I like working with Maxwell's equations in differential form because it makes it easier to derive other equations, whereas if I'm calculating something specifically, I'll use the integral version of them. I mean, I don't think anyone would disagree that Maxwell's equations are really important, and again, they're important in a lot of places. If you do like material physics, or even if you do like if you want to know QED, things like that, Maxwell's equations are important. So I'm going to go ahead and put these in A tier. Next, we have the gamma factor, the Lorentz gamma factor. It tells you in special relativity, and if you're comparing things in different frames, like the time interval between two events, the gamma factor will tell you how much these different frames disagree with each other, because one may be moving relative to the other, so you get time dilation or length contraction equivalently. Usually you see this tacked on to other stuff that's important, like things that you would really measure, like energy discrepancies in different frames, or momentum, things like that, or part of the Lorentz transformation. So this by itself, yeah, I don't know. I'm not like, wow, that's a really cool equation. So I'll put this in C tier. Kepler's laws. God, can I even recite Kepler's laws anymore? You've got the one that says that the area swept between a certain time interval is constant for an orbit. You have the like semi-major axis squared is proportional to the cube of the period. Oh no, I had this backwards. And then you have wait, what's the first one again? Oh, god damn it. And then the orbits are elliptical. Damn it. That's embarrassing. That's not going in the video. I've never been a fan of orbital mechanics. I think there's so many steps along the way. Like if you open Goldstein's classical mechanics and then you go through the orbital section, there's so much like redefining variables that unless you knew that's what you're supposed to do, you probably wouldn't have thought to do that, which makes it really hard to derive a lot of orbital mechanics stuff from first principle, because a lot of it is definitions and like just defining a new variable and then moving forward for that, which I always found really frustrating. So maybe I'm just taking it out on Kepler's laws right now. I'm gonna go ahead and put them C tier because I don't know, I don't use it personally. I'm not like particularly fond of the memories that I have learning Kepler's laws. Yeah, so I'm just gonna keep it there. It's fine. Next we have, I feel like this is gonna have like a particular bias towards things that are relativistically consistent or quantum mechanical in nature. But I guess that makes sense considering I do theoretical nuclear physics. So the next one, we have the Klein-Gordon equation, the first real attempt at making quantum mechanics compatible with special relativity. Not the most useful. I think it only applies for spin zero particles, like scalar particles, scalar fields. But it's also important for like simple toy models that you may use to gain insight about certain observables. So if you use like phi to the 4, phi cubed theory and quantum field theory, that's a scalar particle, so you would probably use Klein-Gordon. So it's not so bad. I'll put Klein-Gordon in C tier. Next we have Heisenberg's uncertainty principle. The uncertainty in position and momentum has to be greater than h bar over 2. Again, very iconic. Could be more general. There's something called the generalized Heisenberg uncertainty principle, which describes how the uncertainties in any two quantum mechanical observables can be calculated in terms of like, I think it's the matrix element of their commutator squared. So if it were in terms of that, I'd probably rank it higher for being more general and therefore more applicable. But this still gets ranked high because it's a very iconic equation, or I guess inequality. So let's go ahead and put this. I'll put this one in B tier. Okay, moving on. We have Gauss's law in integral form. So that's just if you take, if you do the non-medium one here and you apply the divergence theorem, you just get this guy. You integrate the charge density, you get the total charge, and then you have this surface integral. It's probably the first time anyone uses a surface integral in physics, right? When you take introductory E&M, I don't immediately see how you use it anywhere else, because I think in introductory classical mechanics, you could use it because there's Gauss's law for gravity, but at that stage, it's probably too early to be exposed to that. So this is probably the first time you'll ever use like real deal vector calculus stuff, so that's kind of cool. I'll put Gauss's law. It's fun to use too because it's kind of easy, because you only use it if there's symmetry, right? So it's satisfying. It's a confidence booster equation, I think. All right, so next we have the Euler-Lagrange equation. So this is the Lagrangian analog to F equals ma. So if you have a Lagrangian and you substitute it into this second order differential equation for a certain dynamical system, it should give you the same equations of motion as, say, doing F equals ma. But usually for really complicated systems, you'll get there a little bit quicker. So if we look at it, this term here, so the q's are like the coordinates. So this term is basically a momentum. So you have a time derivative of momentum, which is a force. And this term is basically, we have a derivative with respect to x. The term that depends on the coordinates is usually the potential. So you have the force is equal to like the gradient of the potential, or the minus gradient of the potential usually. So I'm biased. I like Lagrangian formalism. I'm going to put this in S tier. It kind of goes hand in hand with Noether's theorem too, because the symmetry is usually a symmetry of the action. So all of this stuff is going to be pretty neck and neck for me. Next we have the entropy, and this is like a statistical definition of entropy because it's in terms of the number of microstates. So the number of ways that a system can be in a specific configuration. So if there's a lot of ways to do that, then it'll probably go to that. That'll be like its equilibrium state, and entropy would be maximized in thermal equilibrium. So this is a pretty important equation. I love statistical mechanics. I'll put this, I'm going to put this one in A tier because it highlights something that you probably first learn about in classical thermodynamics, and it shows you how to relate that to something that's statistical in nature. Next we have Einstein's dispersion relation. If you take the momentum equal to 0, if the particle's not moving, then you just get E equals mc squared. I keep using the word iconic, I'm sorry, but that's kind of what it is, right? So this, if it was just E equals mc squared, I'd probably rank it lower, but this is really important. It kind of defines, you can define your energy momentum 4 vector and what its square is through this equation. I'll probably put it in B tier. I think that's reasonable. Next we have Einstein's field equations for general relativity, Ricci tensor, Ricci scalar, metric tensor, and then the energy momentum tensor. So it shows you how geometry is related to mass distributions. This is a big boy equation. This is like the poster child of tensor calculus. Like if you think of where could you use tensor calculus, like if you want to learn it, this is it. And that's actually the last video of my tensor calculus series. So I'm quite partial to Einstein's field equations. I think they're pretty cool. I'm starting to see like how much all of these equations can really be related to each other, because if you take this stuff, like you have an action over here, the Euler-Lagrange equations, if you have the action that's, say, like the Einstein-Hilbert action, and you vary it with respect to the metric, your equations of motion end up being the Einstein field equations. Forget about the energy momentum tensor, because I think you just have that would be like in vacuum. But in any case, like all of this stuff is so related to each other. These seemingly different fields just have these connections, which I think is pretty cool. I'm going to put this S tier. This is such a cool equation. It's something that you look forward to learning eventually, right? It's like this thing that when you get into undergraduate physics, you have no hope at possibly understanding it at first. And as you go forward in your degree, you start learning a little bit more and more of the formalism. And then it makes sense. It's weird. It's pretty cool. And it's just this other massive entity in physics. The two big things, quantum field theory and general relativity. So it's like in its own regime in that respect. Next we have the Dirac equation. So we talked about the Schrödinger equation being like a non-relativistic theory of the electron. We talked about the Klein-Gordon being a relativistic theory of scalar particles. Now this Dirac equation gives us a relativistic theory of the electron. So finally, we have this consistent framework to describe the electron in a way that's consistent with relativity. And I think that the slash notation is just pretty cool. This just means you basically take the dot product of whatever's being slashed with a certain matrix called the gamma matrix. So that's what that slash notation means. Yeah, that was what really got us started with quantum field theory. And you kind of get it by factoring this guy, which is kind of cool. I'm going to put this one in... this is really important. This is a really important equation. It introduces you to the concept of spinors, which are invaluable in quantum field theory. Yeah, it gives us a theory of fermions, too. That's just... I'm going to put this in S tier. Okay, so we're getting down the list. We only got a few more. So this one is the law of Biot-Savart. Tells you if you have a current and like a displacement vector and the magnitude of the current. So this is like the direction that the current is going. You can calculate the magnetic field. I remember hating this in undergrad. It's inherently harder than E and M because instead of dot products, you have cross products. But I remember having a hard time doing these integrals and figuring out how to define the coordinate system to make it as easy as possible. And then in grad school, you just get over it and you learn it, I guess. So I'll put this one in B tier. This is fine. All right, and then one of the last ones, I think this is the Bernoulli equation, if I'm not mistaken, which is basically like a statement of conservation of energy. There's prettier ways of writing this kind of thing. It's fine. I'll put it in C tier. So this is for like a fluid and stuff. And then last, so I still don't know what this one is. I'll have to take a minute to think about what could be missing. But this one is the definition of the action in terms of an integral over a Lagrangian. I would usually write it in terms of a four-dimensional integral over a Lagrangian density. That way you can really see the Lorentz invariance of everything. But it still stands for what it stands for. This is like at the top of all of this other stuff that we've been talking about. So if you talk about Noether's theorem, you talk about the Euler-Lagrange equations, equations of motion. By the way, the Dirac equation, the Klein-Gordon equation, yeah, those are equations of motion in a sense. So like all of this stuff can be related to an action. It's hugely important. It's not just limited to any one field. You use it in classical mechanics, this principle of least action. You can use it in quantum mechanics if you're particularly masochistic. You can do standard quantum mechanics, not even quantum field theory, using principle of least action, and that'll give you like a path integral formalism. I don't recommend doing that if you're just doing standard quantum mechanics. I think the Schrödinger equation is actually better, but the thing is that the path integral can do it. So if it can do the stuff that's a lot more complicated, like quantum field theory, it should also be able to do the simple stuff. But for the simple stuff, it's kind of like breaking an egg with a sledgehammer. It's just, but yeah, you use it. It's very important. This is probably the easiest choice so far. This is definitely S tier. Everything else kind of follows from the definition of the action, and it's extremizing it, So let's take a look. Are there any last-minute changes that I'd want to do? I think I'm pretty happy with this list. One thing, I think I might put Klein-Gordon B tier, actually. I think I changed my mind on that. And then F equals MA. The more that I think about it, like, this deserves more respect, I think. I think this should probably be A tier. Like, I know it has its limited application, especially for, like, multi-body or multi-system dynamics, but the history of it all, it really did kind of change everything. So I think that should be A tier. I really wish I knew what these equations were supposed to be. So we have like, what are we missing? We have the quantum mechanics, classical, we have a little bit of stat mech, a lot of quantum, we have fluid stuff, sort of. Oh! These could be Navier-Stokes, huh? Maybe. Let's pretend that it is. So where would Navier-Stokes go if that's what this is? It's not going to go very high for me. I didn't mean to put it in D tier. This is going to move somewhere else probably. It's not going to rank very high for me because, one, I don't really care too much about like fluid stuff. And two, even if you try to work other stuff that's related in that form, you kind of have to shoehorn it. Like if you have if you want to describe relativistic objects like energy momentum tensor, it's kind of hard to put that in the language of like a Navier-Stokes equation, because to my understanding it's not really relativistic. So I'll put it B tier. It's very useful for the scope that it's meant to be used for, so we'll put it there. And that's gonna do it. So that is pretty much a skewed distribution towards things that I like more, which I guess is good. It would be kind of bad if all of these famous equations I just kind of shit on. So, sorry, Ohm's law. But yeah, so that's, I guess, how I'm going to rank these things. Let me know in the comments section what you would do differently. Let me know in the comments section what equations are missing from this. In any case, I hope you all enjoyed the video. Remember to check out Eric's channel, linked in the description. Let me know in the comments section if you enjoyed the video, and I'll see y'all there.